So this video, I just want to give a proof of the eigenvalue. I should say the eigenvalue and eigenvector existence. Okay, so in a linear algebra course, usually people will just the professor may just tell you that what's eigenvector. Eigenvector is defined to be mx to be lambda x. Suppose your M is let's say m by m matrices with the real or complex coefficient, and then you are told that you can find such x which is non-zero. So there is this x which is a column vector. So you can view x as a real m times 1 or complex m times 1. And also you are told that there exists some lambda which may be real or complex number, such that mx equals lambda x always exists. And then the important part is that x all can be non-zero, right? So which tell you that the lambda can be non-zero. So if lambda is non-zero, then sure x should be non-zero. Okay, so this is the usual setting. Okay, so now in this video I want to give the proof. So I want to give a proof that basically the existence. Okay, so I want to prove that you can always find such x. So there exists lambda and x which may corresponding to lambda, but x lambda is non-zero, such that mx lambda equals to lambda x lambda. Okay, yeah. So this is the goal. Okay, so let's talking about the usual idea. So the usual the method one, which is the usual idea, is that suppose your m just let's focus on the real part. Okay, go to complex part similar. So let's only work for real part. So if you only works for the real matrix m, right? Then you can prove that if you want to solve mx equals to lambda x, then you are solving m minus lambda identity x equals 0, right? And easy to prove that this will indicate the determinant of m minus lambda is 0, right? So determinant of m minus lambda will be this one will be a polynomial with degree n and complex. In this case, will be real coefficient. Right. So from the theorem, from the fundamental theorem of algebra, So fundamental theorems of algebra tell you that any polynomial with a degree n real coefficient must have n complex roots. Right. So you have n complex roots. Right, so then this indicate the eigenvector, indicate the eigenvalue exists. Right, so lambda always exists. Okay, in general, it's easy to see that if lambda is non-zero, right, x must be non-zero, right? Otherwise, if lambda is non-zero, will indicate that x is non-zero. Otherwise, that any lambda x will. If lambda is non-zero, x is 0, then let's see. Yeah. So the difficult part is that you only prove that lambda exists, right? But there is no guarantee that it seems it's not easy to see that how to show, right, x exists. Okay, so the idea is that once you know that once you pick some particular lambda, right, then the rank of m minus lambda I will be less than n. Okay, so you have the kernel and the rank theorem, right? You know that the kernel of m minus lambda I times plus the rank of m minus lambda I will be n, right? So this is the kernel rank equality. So from here that you know that this guy is less than n, right? So you know that this guy will greater or equal to 1, right? So in this case that and the kernel is a vector space. So from here that we are guaranteed that Maybe I might misspell something, but we are guaranteed that x exists, which is non-zero. Okay, which is yeah, this is approved because the kernel is the non-empty vector space, right? So you can prove that x must exist because you just pick any x belongs to a kernel. Okay, so this is the usual proof. Okay, so let's see the second proof. So method 2. So in the method 2, that only works for the matrix which is real and symmetric. Okay, and in this case that it's easy to prove this because let's consider f to be you just take the Sn minus 1, which is a minus 1 sphere. So for any vector in the Rn dimension, such satisfy their length is 1. So you just take any vector. You just take the set of the forms of sphere, which is x, and x belongs to Rn, and x, which is 1. Okay. Okay, and you start define f, map this to another real number. Okay, so map into R such that you map x into x transpose mx. Okay. So f is continuous. So first notice that f is continuous, right? And Sn minus 1 is compact. Okay, so from extremal theorem, you know that f has maximum and the minimum on Sn minus 1. Okay, so by Lagrange theorem, right, you know that Lagrange multiple, you can define G, which is just f minus xtx, right? Because this is the constraint, which is just x squared, right? And I define x squared to be 1, right? So this is a constraint, and there's a Lagrange multiple. I call it lambda. So gradient G will give you gradient f minus lambda gradient xtx should equal to 0. Okay, so this is gradient xtmx minus lambda gradient xtx, which is 0. Okay, so this part will give you 2x. So simple exercise, and this part, since m is real, m is symmetric, so we'll give you 2mx. Okay, so you get 2mx minus 2 lambda x, which is 0. So you know that mx equals to lambda x. Okay, and so you see from here that we know x is non-zero. And the reason is that the x has a length 1, right? So x must be non-zero. Okay. Yeah, so this is and the lambda exists, right, due to extremal. Okay, and once you do this, then you can project out. So you can project out x and forms the complement of m, right? So you can project out the eigenspace of the lambda. The lambda will form the eigenspace, and you just project out, and so you will get a smaller m. Then you get smaller, and you keep doing, right? And then finally, for the finite dimensional vector space, then you will finish this project. You will finish this proof. Okay, so yeah, so this will prove that the eigenvalue and eigenvector exist. Okay, yeah, so basically this is the second proof. Okay, so let me just end this video by a remark. So there's a small remark that I want to say. So since we only prove that for the real part, right? So for the complex number coefficient, then you just view complex as a real R2, right? So you can define f to be R2n to be R, and define your x map to xt as Hermitian, or basically complex conjugate mx, right? So and you restricted x R2n restricted into S2n minus 1. Okay, and by your extremal theorem, then you can easily prove the same results. Okay, so yeah, this is just the simple video. I just want to make a record of how to prove the existence of the eigenvector and eigenvalue. Thanks.